Conversion of sugar Di-Ketals to bio-hydrocarbons through catalytic cracking over beta-catalysts and fixed and fluidized catalytic beds. Welcome to Journal Club. The latest academic research, explained in plain English. Today we're looking at this paper from MDPI's Journal of Chemistry. It's authored by Cardoso, et al., from the Universidade Federal do Rio de Janeiro in Brazil, and is published open access under a CC BY license. Let's start by translating the title into more accessible language. When you read this title, you can understand it to mean in very simple terms that this paper describes how sugar derivatives can be turned into a type of renewable fuel using a chemical process called catalytic cracking with the help of specific catalysts. Let's expand on that a little. This paper is about turning sugar Di-Ketals, a type of sugar molecule, into bio-hydrocarbons, a type of fuel made from plants, using a process called catalytic cracking. The researchers used a special type of catalyst called beta-catalysts and tested the process in both fixed and fluidized catalytic beds. The goal of this research is to find a sustainable way to produce fuel from renewable resources like sugar. Now we understand the title, which is a good start, but before we can break down the full paper, we'll need to catch up on some terminology, jargon, background information and context. Specifically, there are some key concepts you'll need to be familiar with. Let's define them now. Second-generation biomass. A type of raw material derived from non-food crops that can be used for biofuel production. Catalyzation. A chemical process that involves the formation of acetyls or ketals from carbonyl compounds. Biopetroleum, BP, a liquid produced through the catalyzation of second-generation biomass. DX, a representative compound of BP that was used in the study. Beta-zeolites, a type of catalyst used in the conversion of DX to hydrocarbons. Coke yield, the amount of carbon residue produced during the catalytic cracking process. Space velocity, the rate at which the feedstock, DX and N-hexane mixture, flows through the reactor. Acid sites, active sites on the catalyst surface that facilitate the conversion of DX to hydrocarbons. Fluidized cracking unit, a type of reactor where the catalyst is suspended in the feedstock to enhance the contact between the catalyst and the feedstock. Green hydrocarbon efficiency, the percentage of hydrocarbons, olefin, aromatics, furans, and cycloalkanes, produced that are environmentally friendly. Now that we understand the title and key concepts, we're ready to dive in and break down this paper. In this presentation we're going to attempt to answer 5 questions. 1. What were the researchers trying to figure out? Or more specifically, what was their hypothesis? 2. How did they conduct their experiment? That is, how did they test their hypothesis? 3. What were the results of the experiment? 4. What conclusions did the authors draw from those results? And lastly, 5. Why does this research matter? Why should you care? 1. What were the researchers trying to figure out? The researchers hypothesized that by modifying second-generation biomass through catalyzation, they could produce a user-friendly liquid called BP that could be converted into hydrocarbons using beta-zeolite catalysts, with potential for use as green fuels in future biorefineries. 2. How did they conduct their experiment? The researchers used catalytic cracking to convert sugar Di-Ketals to bio-hydrocarbons. They tested their hypothesis using both fixed and fluidized catalytic beds and analyzed the reaction products in gas, liquid, and coke form. The organic liquid products were analyzed using gas chromatography mass spectrometry (GCMS) and gas chromatography flame ionization detection (GCFID) from Agilent Technologies. The GC system had an HP5 column, and the oven temperature was maintained at 30 degrees Celsius for 7 minutes, ramping up to 170 degrees Celsius for 40 minutes with helium as the carrier gas. The liquid fraction was obtained through condensation, and the liquid amount was determined by the weight difference of the condenser before and after the reaction. 3. What were the results? The researchers found that hydrothermal treatment resulted in a decrease in the number of active acid sites, which reduced the yield of gaseous fractions and increased liquid fraction production. The reduction in acidity achieved a reduction in gas and coke yields, but the deoxygenation was not satisfactory. The use of formatted beta-catalysts improved the deoxygenation of Di-Ketals and increased gasoline octane, but it also led to higher coke and dry gas yields. The fluidized bed process allowed for the use of a higher amount of deactivated zeolite, increasing the total number of acid sites without increasing the acid site density. The researchers observed that deactivated zeolite did not completely convert Di-Ketals, but the formatted beta catalyst was able to achieve 100% conversion. The use of the catalysts also resulted in a decrease in oxygenated products, leading to a higher yield of aromatics and hydrocarbons. 4. What conclusions did the authors draw from their results? The researchers concluded that beta zeolite can produce high-value bio-hydrocarbons from a model diacetyl of biopetroleum found in sugarcane bagasse in both fixed and fluidized bed reactors. The catalytic system containing beta zeolites was examined, and reducing the acidity of beta led to a decrease in unwanted byproducts, although DX could not be completely converted into hydrocarbons in the fixed bed unit. The beta catalyst performed better than pure zeolite in the fixed bed unit, with even less interference and decreased oxygenate yield, but slightly increased coke yield. The deactivated catalyst also showed significant deoxygenation improvement in an FCC unit, indicating the potential of beta-containing catalysts for use in a biorefinery. 5. Why does this research matter? The importance of this paper lies in its contribution to the development of sustainable alternatives to fossil fuels, which are becoming increasingly scarce and environmentally damaging. We hope you've enjoyed this Journal Club presentation of conversion of sugar Di-Ketals to bio-hydrocarbons through catalytic cracking over beta catalysts in fixed and fluidized catalytic beds. If you'd like to read the full paper yourself, which we encourage you to do, you can find it at DOI 10.3390/Chemistry 5010035.